And last week, or the last time we met, for this class specifically, we discussed permutations and combinations. I am pretty sure members are trying out numbers from the question bank, because I'll tell you with quantitative techniques, there's no shortcut. As long as you don't practice, as long as you don't do questions, as long as you don't consult, as long as you don't read, you're going to find challenges with this paper. So it is important that you focus. It is important that you read. It is important that you discuss with the colleagues. It is important that you attend the revision classes. We had decided that starting April to May, all revision classes will shift to be physical, all. It's because I want to see you around. I want to see who are the people, how you guys are picking up the stuff. You know, sometimes it becomes very hard for me to tell who has understood a concept and who has not, especially when you are conducting these classes online. That is why you see that when we are conducting these classes online, at some point, we move a little faster as compared to the physical classes, because I cannot see you, I can't judge, I can't tell who has understood the concept and who has not. So it is likely, unless otherwise, that all the remaining revision classes are going to be conducted physical at the college. So I would prefer that you all come out. Let's become a little more serious, because indeed we only have this month. In terms of syllabus coverage, we still have some significant topics, close to 5 or 6. So we need to indeed devise time. In fact, I had wanted to propose that we do have at least a class on Wednesday. On Wednesday, we can decide to have a class. And then we see how we can push. Otherwise, we still have a lot to cover, and yet we still have a lot to revise. So today we are looking at, we are supposed to cover binomial distribution. Most of the distributions, given the time that is available, we shall cover and see how far we can move. Otherwise, my plan is to cover binomial distribution, Poisson distribution, and normal distribution. Including the approximation, both for a Poisson and a binomial, normal distribution. So let's look at the binomial distribution. The binomial distribution. Binomial distribution. Okay. Binomial distribution. Just a minute. Okay. Now, from class, we have already seen or looked at what we call the discrete and continuous distribution. And we said the discrete distributions specifically look at situations where we have data that is specific, data which can be obtained from countable domains. We said that with discrete distributions, we shall always obtain our values, and these should always be specific. They are obtained through counting. If I want to know the number of students attending this class, I can ably tell that there are 13, there are 20, meaning that the 20 is specific. The 20 is very, very accurate, like it is one value. It cannot take any range. If you talk of the number of classes remaining, you can ably say that there are, say, 15 classes without saying whether they are ranging between this and this. The number of televisions sold, it is a discrete value which is very specific, finite. So with such distributions, you're able to tell which is which in terms of size, in terms of numbers. Those are discrete distribution. So every time we are looking at a discrete distribution, we are actually looking at a statistical distribution that describes the probabilities of possible outcomes of a discrete random variable. In other words, we shall be obtaining probabilities of each possible value that the random variable can take. The probability, each possible value that a random variable can take. And some of these discrete variables that we have, which give us the probabilities of each possible value that a random variable can take, we have the binomial distribution, we have the Poisson distribution, there is what we call hypergeometric distribution, but we don't cover it here, etc., etc. So these distributions are used to model situations where outcomes are distinct and countable. Where outcomes are distinct and countable. For example, when we look at binomial distribution, we are going to see that in any given experiment, that we perform, we expect two different outcomes, the probability of a success and the probability of a failure. So we are saying that under these distributions, we shall be looking at situations where the outcomes are very distinct, where the outcomes are countable, they are known. For example, if I talk of the number of, if someone tosses a coin, the outcomes are two. It is either a head or a tail. So with those two, if, for example, your intention is to obtain a tail and you toss the coin, if the tail comes up, then you have a success. If the tail does not show up, then you have a failure. So the outcomes are just two. And the number of times the experiment has to be performed is very, very specific and known. So those are the different situations that we are going to look at that would lead us into these different distributions where we have countable and distinct situations or outcomes. So let's start with the binomial distribution. The binomial distribution. A binomial distribution is a discrete distribution that bears the following characteristics. One, these are characteristics. Now, for purposes of understanding this binomial distribution, the Poisson distribution, the normal distribution, and any other distribution, it is important that you clearly understand what it is and also the various characteristics that underlie such a distribution. So it is very important that you clearly understand what these distributions mean and the characteristics that underlie each of these distributions. So the binomial distribution, we are saying that it is a discrete distribution. I've explained what a discrete variable is. It is a discrete distribution which bears the following characteristics. One, the number of times an experiment is performed is known with certainty. The number of times this experiment is to be performed are known. They are clearly known to you. You know that if I'm going to perform, I'm going to toss a coin or a die. Is it a die or dice? You going to know, you know the number of times that experiment is going to be performed. So one of the characteristics, we are saying that the number of times the experiment is performed unknown with certainty. So you know how many times a given experiment shall be performed. So if you're looking out for a question, you're wondering whether it is a binomial, a Poisson, or any other distribution, look out for that characteristic. Check how many times have I got to perform this experiment. There are 4 times. There are 6 times. There are 3 times. So as long as you can ascertain that they are fixed, then you can link it to the binomial distribution. Number 2, every trial results into 2 outcomes labeled success and failure. Every trial results in 2 outcomes, i.e., success or failure. So when you perform an experiment in a given trial, you expect 2 different outcomes. It is either a success, which is P, and failure, which we normally call Q. These are the 2 different outcomes expected in any given experiment. Number 3, the outcome at each trial is independent of the outcome in any other trial. The outcome of each trial is independent of the outcome in any other trial. The outcome of each trial is independent of the outcome in any other trial. For example, if you toss your coin twice, the fact that you have a head in the first trial does not affect what outcome will come in the second trial. So you cannot say that in the first trial I have a head, so the fact that I have a head, even in the second trial I will have a head. So the outcome in one trial does not affect the outcome in any other trial. And lastly, the probability of a success or failure must remain the same throughout the experiment. Number 4, the probability of a success or failure must remain same in or throughout the experiment. The probability of a success or failure must remain the same throughout the experiment. So those are the four different characteristics that underlie a binomial distribution. So every time you're looking at a given question, check out for these characteristics. Are the number of times known to you with utmost certainty? If you perform this experiment, do you expect only two different outcomes, failure or success? Does one outcome have an effect in the outcome in the other trial? Is there any changes in terms of probabilities? If it is a probability of a success, does it change throughout the experiment? The answer is a no. Then you can easily attribute it to binomial distribution. Binomial distribution. So we can say, given a binomial distribution, or given a binomial situation with a probability of a success, in bracket P, at any trial, N, the number wait a minute, the probability should be the probability. The probability of obtaining successes is given by P of R is equal to any combination R. I believe we all remember how to come up with that, times probability of success to the power R times 1 minus P to the power N minus R, to the power N minus R. Or probability of success of R is equal to any combination R times P to the power R. 1 minus P is the same as Q to the power N minus R. You say where Q is equal to 1 minus P. Q is equal to where Q is equal to. So we can define some of these events where any number of times an experiment is to be performed, number of times an experiment is to be performed. Number 2, P probability of success, Q probability of failure, and R the number of successful events in an experiment. In an experiment. Number of successful events in an experiment. And we say these can be these can be values starting with 0, 1, 2, etc. 0, 1, 2, etc. So whenever we find a question that is targeting binomial distribution, first of all, we must look out for the characteristic, and then you see, is there a chance that I'm supposed to use binomial? Would it be Poisson, etc, etc, etc? So you should be in a position to obtain them, and you check out for the real value. Real value. So let's look at an example. Let's get an example. Check page 168. We have a question there. Page 168 of the reader. For those of you who have study materials, many more are not yet here. When is your network now okay? Is Wanika still here? Christopher? Are you now better? I hope you're now able to hear us properly, because I've seen your complaint. Your network was very poor and we are not able to follow through. I don't know whether your network is fine. But just in case it's not, then you let us know. Example 1. Example 1. The probability that a machine will need correcting adjustments during a day's production run is 0.2. The probability that a machine will need correcting adjustments during a day's production is 0.2. If there are 6 of these machines during a particular day, find the probability that 1, no machines need correcting. 2, just 1 machine needs correcting. 3, more than 2 machines need correcting. Let's try to fit this question into a binomial situation. 1, we said the number of times an experiment is to be performed is known with certainty. So when we say, if there are 6 of these machines running in a particular day, the machines cannot become 7. The machines cannot become 10. They are 6.
6.
So they are saying that the number of times the experiment is to be performed, it is known, because we are saying that if there are 6 of these machines running in a particular day, meaning that in a particular day we are focusing on simply 6 machines. So the number of times this experiment is to be performed can be linked to the number of time, or to the number of machines in this case that are actually going to be used. Number 2, the probability that a machine will need correcting adjustments during a day's production. The 6 machines that we are looking at are going to be used during a day. That is why they are talking of a day's production. And they are saying that the probability that any of those 6 machines will need correcting adjustment is 0.2. And when you check the question, they are talking about, again, the machines that will need correcting. So we are saying that the probability that a machine will need correcting adjustments during a day's production is 0.2, and that is the probability of a success. Remember, we said for any given experiment that we perform, there will be 2 probabilities or 2 outcomes. Now, the first outcome, that is when the machine needs correcting adjustment. The second outcome, when the machine will not need correcting adjustments. So the probability that a machine will need correcting adjustment during a day's production is 0.2. So our N in this case, we have said that it is 6, and our P is 0.2. That is when the machine needs correcting adjustments. And then if this is that, then our Q would be 1 minus P, which is 1 minus 0.2 to get a 0.8. So the probability that the machine will not need any correcting adjustment is 0.8. The machine that the probability that no machine will need any correcting adjustments will be 0.8. That is the probability of failure. Now, why do we say that the probability of a success is 0.2? Or why do we say that the probability of a success is linked to correcting adjustment, or is linked to a machine needing correcting adjustment? It's because the examiner says that the probability that a machine will need correcting adjustment, that is the probability of a success. It is what we are looking at. We will need, meaning that the event of needing correcting adjustments gets us into the probability of a success. Now, the event that no machine will need is the failure in this case. Is the failure in this case. The failure in this case. Now, the question is, find the probability that no machines need correcting. Find the probability that no machines need correcting. You remember we said that our R, the number of successful events in an experiment, and this could be in the form of a 0, 1, 2, 3. Now, this probability of a success will not change throughout the day. The probability of a failure will not change throughout the day. And if there is a chance that one machine needs correcting adjustment, it doesn't mean that even the other machine will need the same kind of correcting adjustment. So when you try to look at those different characteristics, indeed, they point to a binomial distribution. So let's try to answer this. Part 1, no machine needs correcting. No machine needs correcting. No machines need correcting. So it means we want the probability when R, the number of events, is equal to 0. No machine needs correcting. Not forgetting that, remember, probability of R is equal to n combination R, P to the power R, Q to the power n minus R. So our n is a 6. Probability when R is equal to 0, no machine needs correcting, will equal to 6 combination is 0, because R is a 0, times P, which P is 0.2 to the power 0, times Q, which is 0.8 to the 6 minus 0. So this will be 6 combination is 0 times 0.2 to the power 0, and any number to the power 0 is a 1 times 0 to the power 6. That will give us our probability. I believe members know how to press that on their calculator. We say the button which has combination is the division sign, division button, or the button which has division sign. Combination is 0, and your calculator has the ability to get this answer at once. Your calculator has the ability to get this answer at once. So for me, when I try to press it on my calculator, I get 0.262. 0.262. That is the probability that no machine needs correcting, adjusting. That is the probability that no machine needs correcting, adjustment. Number 2, just one machine needs correcting adjustment. That is when we have probability of R equal to 1. Again, this will be any combination R or R n minus R. So 6 combination 1 times 0.2 the power 1 times 0.8 power 6 minus 1. Something that gives us 6 combination 1 times 0.2 times 0.8 to the power 6, to the power 5, sorry. Six combination 1 times 0.2 to the power 1 and 0.8 to the power 5. For me, I'm getting 0.393. I hope members are trying to press. We are getting a 0.392. 0.392. 0.392. Part 3, Part 3. The probability that more than 2 machines will need correcting, more than 2 machines will need correcting. More than 2 machines will need correcting. More than 2 machines will need correcting. The probability that more than 2 machines will need correcting. Now, if we talk of more than 2, there are 6 machines. It means the probability we are interested in, probability of R greater than 2, which is equal to the probability of R equal to 3 plus the probability of R equal to 4 plus the probability of R equal to 5 plus the probability of R equal to 6. Those are the probabilities that we are interested in. However, by use of numbering, we can have it change. If this is 1, this is 2, this is 3, this is 4, 5, and probably 6, and this is 0. When I put a line here, here is the probability of R greater than 2. Whichever that you have this side, after the line, is probability of R greater than 2. And whatever that I have this side, going this side, it is the probability of R less or equal to, less or equal to 2. Less or equal to 2. The other side, it is greater than 2. This side is less or equal to 2. So when I have probability of R less or equal to 2, plus the probability of R greater than 2, this must always give us a 1. That when you have this plus this, you must always get a 1. Do we understand that number line? Are members able to understand what I'm writing there? Yes or no? I am saying from this point here to 0, it is the probability of, okay, by simply looking at this, it is PR less equal to 2. It is equal to less than 2. But from here going the other side, it is R greater than 2. Because we have a re, this side is a 3, 5 is 6. This side each of 1 is 0. So this side is less than 2. But because the question is talking of more than 2 machines, meaning that it is, we are getting 3, 4, 5. That is the situation when we have more than 2. That is why we were picking 3, 4, 5, and 6. So when I add this plus this, indeed it should give us, in probabilities, the sum of all the possible outcomes available should always give you a 1. As long as you add up all the possible probabilities, you will always get a 1. So the probability that R is less or equal to 2 plus the probability of R greater than 2 is equal to a 1. Any question? Any question? So these are the 2 ways. I am interested in this. That means the probability of R greater than 2 will equal to 1 Then this one, I'm going to take it the other side. I'm going to take it this other side. Minus the probability of R less or equal to 2. And the probability of R less or equal to 2, it would mean that I have 1 minus the probability of R equal to 0. Probability of R equal to 0 is less than 2. Plus the probability of R equal to 1, it is also less than, a 2, plus the probability of R equal to 2, because we said less or equal. These are the only probabilities that I'm subtracting from there. And once I have subtracted those, I should be in a position to get the probability of R greater than 2. So I'll be having 1 minus probability of R equal to 0 is already known. We have already determined it here as 0.262 plus the probability of R equal to 1 is here 0.9 plus the probability of R equal to 2. We haven't done that, so we shall get it as combination 2 times 0.2 to the power 2 times 0.8, 6 minus 2. So that means I will have 6 combination 2 times 0.2 to the power 2 plus 0.8 to the power 4. So what do you get? This is 1 minus 0.262 plus 0.393 plus 0.246. So 1 minus, open brackets, 0.262 plus 0.393 plus 0.246, close brackets. .393. For me, I'm getting a 0.099. That is the probability of R greater than 2. .099. But another person who has used this, and you get for all these, you should be in a position to get the same probability. Probability of R. Now with this, it means you just have to substitute in each of them. In other words, you could say, oh, the probability of R greater than 2 would be 6 combination theory 0.2 to the power 3 times 0.8 to the power 6 minus 3 plus 6 combination 4 times 0.2 to the power of 4 times 0.8 to the power of 3 minus 4 plus 6 combination 5 times 0.2 to the power of 5 times 0.8 to the power of 6 minus 5 plus 6 combination theorem type 6 combination 6 times 0.3 to the power 6 times 0.8 to the power 6 minus 6. These should be in position to give you a 0.099. So any of those two can do for you. However, I normally recommend this. This is, for example, in this case, assuming machine is what 15 machines, would you go ahead and get for 3 up to 15? It becomes a little hard. So make sure that you're able to understand the first bit of that probability. Are we together, guys?
Yes.
That is nice. So if that is done, we can look at there is example number 2 in your books, which has calculate and tabulate the probabilities of 0, 1, 2, 3, 4 successes for a binomial situation with n equal to 4 and p equal to 0.25. I think that one all of us can do. We just need to do this. These are the error successes, and these are the probabilities of error. They are telling us to find for 0, 1, 2, 3, and 4. These probabilities here, given that n is equal to 4 and p is equal to 0.25, meaning that q would be 0.75. So for each of these, you go ahead as probability. So when probability r is equal to 0, then you would be substituting in 4 0.25 to the power 0 times 0.75 to the power 4 minus and get 1 4. Use it when you're getting for 1, 2, 3 up to 4. You'll be in position to calculate and tabulate the probabilities of those different successes. So you get for P, R is equal to 1, P of R is equal to 2, P of R is equal to 3, and P of R is equal to 4. All those are various probabilities that need to be obtained. We have binomial distribution versus normal distribution. You know, it is not easy. We can never talk about binomial distribution and we do not talk about normal distribution. We do not talk about normal distribution. So the main difference is that a binomial distribution is discrete, like we said, whereas normal distribution is continuous. Whereas a normal distribution is continuous. So where you have a binomial, you expect to have a finite number of events, numbers which are known, the events which are very known, whereas under normal distribution, it has an infinite number of events. So in this case, the sample size of the binomial distribution is very large. Then the distribution curve of a binomial is similar to that of a distribution curve. In other words, the size of the sample, under normal distribution is expected to be large. And once it is large, there are cases where we shall see that a binomial distribution approximates a normal distribution. We are going to get there, and we shall be in position to see how a binomial is calculated using normal distribution. Mean and variance of a binomial. Mean is equal to NP and variance is equal to NPQ. Where Q is equal to 1 minus P. 1 minus B. 1 minus P. 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 Example 2. Example 2. A crate of items is rejected if more than 2 items are found to be defective in that crate. A crate of items is rejected if more than 2 items are found to be defective in that crate. Otherwise, he accepts it. A crate items is rejected if more than 2 items are found in a defective in a crate. Otherwise, he accepts it. It is known that 5% of these types of items received are defective. If a random sample of 20 items is taken from the crate, calculate the proportion of crates that will be rejected. Calculate the proportion of crates that will be rejected. calculate the proportion of requests that will be rejected. Now, when you talk of a proportion of requests that will be rejected, it is almost the same way of saying that calculate the probability that a single crate will be rejected. Because we said that a crate can only be rejected if more than 2 defective items are found in it. As long as we find 2, as long as we find 2 or more than 2, in fact, if more than 2, a crate of items is rejected if more than 2 items are found to be defective in that crate. So when we say the probability that more than 2 items will be found in a crate, that is the same as saying that we determine the proportion of crates that will be rejected. Now, the proportion of crates that will be rejected depends on the number of defective items that we have per crate. So it is the same as saying the probability that a single crate will be rejected. Probability that a single crate will be rejected. Probability that a single crate will be rejected. So, which is equal to the probability that a crate bears 2 defective more than 2 defective items in a crate. The probability that a single crate will be rejected is the same as having a probability of more than 2 defective items in a crate. So remember, our n in this case was given as a 20. And when they talk of more than 2, it means you're going to move from 2, more than 2, 3 up to 20. Like I was saying in this example, that you just don't need to have all of them, because we can always use the number line for purposes of removing those difficulties. So in this case, the probability that R is greater than 2 is equal to 1 minus the probability of 0 plus probability of 1 as a probability of 2. Or the probability of R equal to 0, probability of R equal to 1, probability of R equal to 2. So that is what you're going to subtract from 1. It is what we shall subtract from 1. So 1 minus 20 combination is 0 times 0. The probability of a success, they told us it was 5%. It is known that 5% of these types of the items are defective. So this is a 0.05, the power 0 times 0.95 to the power plus, don't forget that this is a 20 to the power 20, because we shall be getting 20 minus 0, which is 20. Plus, I think I need to shift to the next page and say probability of R greater than 2 is equal to probability of so we can substitute in the formula and then obtain those.
Excuse me, Mr. Fred.
Yes.
Yes, I'm inquiring where we got the 0.95.
0.95.
Yes.
Do you have the question?
Yes, I do.
What is the probability of a success? They said it is known that 5% of these types of items are defective. So if the probability of success is 5 out of 100, which gives us 0.05,
Yes.
probability of a failure, which is Q, is equal to 1 minus P, which is equal to 1 minus 0.05 to give us 0.95. Is that okay?
Yes, sir. Thank you.
Okay. So I want us to get this 1 minus 20 combination is 0 times 0.05 to the power 0 times 0.95 to the power 20 plus, when R is a 1, it would be 20 combination 1 times 0.05 to the power 1 times 0.95 to the power 19 plus 20 combination 2 times 2 times 0.9 to the power 18. So you get that answer. This would be 1 minus, open brackets, 20 combination 0 times 0.05 to the power 0 times 0.95 to the power 20. Zero point 358 plus, now this 0.358 is for this first one here, then plus for the second one, that is 20 combination 1 times 0.05 to the power 1 times plus lastly, two into two So as you add all these probabilities, you should be in a position to obtain the probability which you're going to list there. So I have 0.358 plus 0.377 plus 0.1887. So minus 0.9237. So my answer is 0.0763. So that is the probability that more than a single item will be rejected. So the other person would say, since they are talking of more than two, you could be adding up from 3 up to 20. Something that will take you a lot of effort. Something that will take you a lot of effort. And let's examine, and it requires you to do it that way, for which I am very sure it's possible. Is that other example? Part B of the same question says, calculate the mean and the variance of the number of defective items in a sample of 20. Since our n is equal to 20 and our p is equal to 0.5, our NP can be obtained. At the end of the day, we want us to determine the mean and the variance. But we all know that mean is equal to NP. So our n is a 20 times p, which is 0.05, to give us 20 and 0.05, 1. And the variance is equal to NPQ. And times so this is variance 20 times 0.05 times 0.95. Which is equal to 0.95. In your study text, you have a third example. We can interpret it and you do it in your free time. A company minibus has 7 passenger seats and on a routine run on a routine run, it is estimated that any passenger seat will be filled with a probability of 0.42. Determine the mean and the standard deviation of the binomial distribution of the number of passengers on a routine. Calculate the probabilities at 2 decimal points that on determine the probability, determine the mean and standard deviation. Determine the mean and the standard deviation of a binomial distribution of the number of passengers in the routine run. Calculate the probability at 2 decimal points. 1, there will be no passengers. 2, there will be just 1 passenger. 3, there will be at least 3 passengers. So in this case, if at all we want to come up with the various items in here, the company minibus has 7. So the number of times the experiment has to be performed is 7. Those are times, 7 times. And the probability of a success is equal to 0.42, meaning that the probability of a failure will be a 1 minus that is 42. Q is equal to 0.58. Q is equal to 0.58. Find the probability part 1, mean we all know how we get it, is equal to NP. And the variance NPQ. And the variance NPQ. So those ones you can easily substitute in, and it is just a matter of multiplying those. Calculate the probability at 2 decimal points that on a routine run, there will be no passengers. So when they say no passengers, they want the probability that R is equal to 0. There will be no passenger, there will be just 1 passenger. R is equal to 1. And the 3, there will be at least 3 passengers. Probability equal to R is greater than or equal to 3, because they said at least. The minimum is a 3. So it is greater or equal to 3. Those are the probabilities which must be determined to answer this question. So go ahead and determine those probabilities. Under a binomial distribution. Under a binomial distribution. Can we look at a Poisson distribution? Our distribution number 2, the Poisson distribution. So we have looked at binomial distribution, and we said it is a discrete distribution. The same thing happens to a Poisson distribution. And with a Poisson distribution, it is going to be used contrary to the binomial distribution, where we normally expect to have our sample space, that the number of times a given experiment is performed, to be small. With the Poisson distribution, the sample space is quite very large. The sample space is quite very large. So we are saying that a Poisson distribution happens when the nature and existence of events are random and rare. Are random and rare. For example, assuming you're looking at a hospital and you want to determine, or you're looking at the number of calls received within the hospital. The number of calls that come in are coming from different angles and different positions or areas. So where these calls, the people who are making the calls, assuming it is Mulago Specialized Hospital for the women, those people will receive calls from the entire Uganda and even outside Uganda. So the nature and existence of events, where these calls are coming from, it is quite very, very random and rare. In other words, it is very, very big. If someone asks you to look at the accidents happening in Uganda in a week, the sample space is very big to the extent that you do not know how many accidents are going to happen. In the event of cause, the cause are going to be many to the extent that you will not tell how many these calls are going to be received on a given day. Imagine you're looking at a supermarket, a very busy supermarket. You cannot tell how many different customers will come in a supermarket on a given day or in a given week. So with the Poisson distribution, we look at such situations, such scenarios where the nature and existence of events are random and rare. We are not so sure of how much is going to happen, how many are going to come, how many are going to be received. But because of experience, this is something that you're handling, that you're looking at on a daily basis. If they are calls and you're the customer care who is receiving calls, from experience, you can say that on average, these are the number of calls I expect to receive in a given day. On average, these are the number of accidents that I expect that can happen in Uganda in a given week. On average, from past experience, you can tell how many customers can visit a supermarket in a given day. So we can only determine that average, that mean, representing the total number of items that are going to visit a given area or that are going to be received within a given area. That is why we say that the nature and existence of events are random and rare. The interval or time or space is defined. The interval of time or space is defined within which these events are going to occur. You remember I've been giving an example and I say the number of customers received in a supermarket in a given week. So the interval is defined, it is within a week. The number of accidents happening in Uganda on a given day, So the interval or time space is a day. Is a day. So ideally, those are some of the statistics that we can look at for purposes of knowing a Poisson distribution, for purposes of understanding a Poisson distribution. So we normally say that a Poisson distribution is a probability distribution that describes the number of events occurring in a fixed interval of time or space, given a constant of average. I think we can write this. A Poisson distribution is a probability distribution that describes the number of events occurring in a fixed interval of time or space. Given a constant average rate of occurrence. This is what I've told you, I've been explaining that you're not so sure, but from experience, you can easily tell that on average, these are the ones I expect. And that means, in any case, if you're looking at a Poisson distribution, you always be required to find the mean. You always be required to find the mean, the average. And the events happening normally are independently happening. You do not know. None of the events is actually depending on the other. If there are if there are various members calling, one calling does not mean that even the other person will call. Normally we say it is characterized by one parameter, often denoted by lambda or m or any other value that means mean, which represents the average rate of occurrence of events. The average rate of occurrence of events. So you have seen we have some examples in terms of applications, the number of deaths by horse kicking, the birth defects and genetic mutations, car accidents, traffic flow and ideal gap distance, number of typing errors on a page, and then failure of a machine in 1 month. etc. All those are different applications that can be used to look at a Poisson distribution. So we normally say, given a Poisson situation, with M equal to mean number of events per interval, the probability of R events occurring is given by so the probability of R events is equal to E to the power negative M times M to the power R over R factorial over R factorial over R factorial. So you'll be in a position to obtain your Poisson distribution. The Poisson distribution. So that is the situation. And here we are saying where R can be 0, 1, 2, 3, etc. 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 So at any one moment, for a Poisson, you'll be required to find the different R events or R successes. Then you'll be required to find the average based on experience, how much, what is the average of that event occurring, how many times does it occur on average. That is why most of the questions will talk about on average. On average, you'll be in position 2. Okay, guys, just a minute. Just hold it briefly. I just need to finish up something here. Okay. Continue. Let's continue. Let's continue with our class. So let's look at an example. At all times, expect to have your average. In fact, in most cases, the questions that are targeting Poisson distribution, you already find this on average. It is normally very, very key. But the one thing you have to note that Poisson distribution looks at a sample space that is big. Big and random. Big and random. So it is not easy for you to define that sample space. You can't say that there are these kind of events. You can't say that these are the number of calls that I'm going to receive, but you can always tell them in an aspect of average. And hence this M here, where the M, in this case, from the above, E is the exponential value available on your calculator. Now I'm doing this in a way that you see it on your calculator. Those of you, when you try to check your calculator, you see there is a button which has in button which has in, it is the third placed button on the right, just below on. It has EX here, e to the power X, then oct E. Do you see that button? So when you press shift and that button, the E should be in position to appear on your calculator. When you press shift, that is the topmost left corner button. You press it and press this one, this first, and then you follow with that. You'll be in a position to have E. It will be coming on you, displaying on your screen. It will display on your screen. So let's look at an example. That example is on page 170. That example is on page 170. It is on page 170. And the example reads, customers arrive randomly at KK stores at an average rate of 3.4 per minute. Customers arrive randomly at KK stores at an average rate of 3.4 per minute. An average rate of 3.4 per minute. At an average rate of 3.4 per minute. So, assuming customers' arrivals follow a Poisson distribution, calculate the probability that A, no customers arrive in any particular minute. This M is mean, and here these are the successful events. No customer arrives in any particular minute. No customer arrives in any particular minute. So, having seen that, we can now say that the probability of R is equal to the probability of R is equal to e to the power negative m, m to the power r over r factorial. So in this case, we want the probability of no customers R is equal to 0, meaning that we are going to substitute in this, where m has been given as 3.4. In the question, they said at an average rate of 3.4. At an average rate of 3.4. So that gives us can substitute in this e to the power negative 3.4 times 3.4 to the power r, which is 0, power r, which is 0, over 0 factorial, over 0 factorial, over 0 factorial, 0 factorial, 0 factorial. So you can press that on your calculator. And we have this, the other button I told you, shift, lean button. We have the E minus 3.4, the way it is. Just put it on the calculator the way it is, minus 3.4 times 3.4 to the power 0 divided by 0 factorial. It gives me a probability of 0.033. 0.333. That is the probability that no customer arrives in a particular minute. No customer arrives in any particular minute. Part B, exactly one customer arrives in any particular minute. That is the probability when R is equal to 1. Probability of R equal to 1. Again, I'll have the same thing. E negative 3.4 times 3.4 to the power 1 over 1 factorial. Over 1 factorial. So I'm just changing where there's 0 and I'm putting 1 factorial to give us a probability of 0.1135. 1135. 1135. Part C, 2 or more customers arrive in any particular minute, in any particular time. 2 or more customers arrive in any particular time. They are talking of two or more. Now here, in this case, if you don't understand to use the number line, you will not answer this. Because they are talking of 2 or more customers. But we do not know the number of customers since we said the sample space is quite very large. The sample space is quite very large to the extent that we can only take the average. We can only take the average. So in this case, you've got to know how to use the number line. If we say 2 or more, then we have to go ahead and obtain what values shall we be taking. Now, this is what I'm saying. Assuming this is my number line. Assuming that is my number line. This is 0, 1, 2, 3, 4, up to n. We don't know the number up to n. We don't know the numbers. Therefore, if they talk of 2 or more, I would draw a line here and I say this is the probability that R is greater or equal to 2. This time around, they are talking of 2 or more. 2 or more, meaning that even the 2 is inclusive. Meaning that even 2 is inclusive, 2 or more. So if that is the case, it means this side we have P, R is less than 2. Because the 2 is already taken. So the 2 is not part of this one here now. It is part of this. But I'm saying that when I get the probability of R less than 2, plus the probability of 2 or more R greater or equal to 2, this must always give me R greater or equal to 2. Probability of R greater or equal to 2, which shall be 1 minus the probability of R less than 2. And the probability of R less than 2, probability of R less than 2 is actually probability of R probability of R equal to 0 plus the probability of R equal to 1. Probability of R equal to 1. Those are the only 2 probabilities. So in this situation, our probability of R greater or equal to should be 1 minus, open brackets, the probability of R equal to 0 plus the probability of R equal to 1. So we know that the probability of R greater or equal to shall equal to 1 minus, open brackets, the probability of R equal to 0, that is no customer. We have already determined this, which is a 0 point. Okay, let me put it here. Members might find it a little hard to navigate. This is E power negative 3.4 times 3.4, 0 over 0 factorial plus E negative 3.4 times 3.4 over 1 factorial, the power 1. So these two we have 1 minus 0.033 plus 0.11 what? 35. 135. So 1 minus 0.333 plus 0.1135, which is 0.4465. And so when we get 1 minus that, answer shall be getting is 0.5535. 5535. 5535.
Excuse me, Mr. Fred.
Yes.
I'm inquiring why 2 is not inclusive. 2 or more customers. Yes.
2 or more customers.
Yes.
have said it is a 2 or more customers. And right from here, we have said that from here, this is our 2. This is where we have our 2. The probability that we are interested in, it is a 2 or more, meaning that even the 2 is inclusive, 2 or more. You get it?
Yes.
Now, if I'm to use this number, it means from this line going this side, it is 2 or more. Then from before you reach this line, it is less than 2. So less than 2, if I'm to get the probability of 2 or more, 2 or more, it simply means I'll have to get 1 minus the other bit which is remaining. Mutually exclusive events, you remember, we have just looked at them. This would be R less than 2. Because this side is less than 2, the other one includes the 2, takes the 2. The 2 cannot appear in 2 different areas. We cannot have our 2 being part of this and the same part of it. That is why it is less than 2. And if it is less than 2, the only values that we have available, which are less than 2, is the 0 and 1.
Yes.
Okay. So what we are looking for is probability of R is greater than 2. That is why we are getting it is 1 minus anything which is less than 2, which is this. Minus anything less than 2. And anything less than 2 is the probability of R equal to 0 and the probability of R equal to 1. Those are the only. So having done that, that is why we're getting this probability.
Thank you, sir.
You're welcome. So that is another situation of how to determine Poisson. Part D, it has a part D. It has a part D. Part D says 1 or more customers arrive in any 30-second period. Yes?
The answer should be 0.8173.
0.8173. Wait, it is 0.0333 plus 0.1136. Okay, 1 minus answer. Oh, how did I add and subtract? This is wrong. That should have been 0.1469. And the final answer being, okay, 0.8531. Is that what you have?
Yes.
So it is that. Part D, thank you. Part D says, calculate the probability that 1 or more customers arrive in any 30-minute second. Calculate 1 or more customers arrive in any 30-minute second. Now, in this case, the interval has been changed to 30 seconds. We have had the time interval is changed to a 30 seconds, meaning that even the average rate in which the customers are arriving is going to be changed. So it has been changed by half from 1 minute to 30 seconds. So that means even the mean must be adjusted to half of the previous mean that we had. So need to adjust the mean as well to half, which is 0.4 times a half, giving us 1.7. So that is the average rate in 30 seconds. That's the average rate in 30 seconds. By this time around, they are talking of one or more. One or more. Again, we have to use a number line because we know that this is a Poisson distribution where we have a very large sample space. We do not know how many are going to arrive. Instead, we can only take an average rate. So what I'm going to do, if I'm to come up with a number line, I have 1, this is 0, 1, 2, 3, etc. If they talk of 1 or more, the line is drawn at 1 because that is where we have our 1 or more. So this side it is R is greater or equal to 1, and this side is R is less than 1. R is less than 1. So for me to get probability of R equal to 1 with 1 inclusive, it's going to be 1 minus the probability of R less than 1. So 1 minus probability R less than 1 is just the probability of R equal to 0. That is the only probability that we have. So it will be 1 minus this probability we already have. So we have E to the power negative 1.7 times 1.7 to the power 0 over 0 factorial. And then this will give us, so if I try to put in a calculator, I'll have my E to the power negative 1.7 times 1.7 to the power 0 divided by 0 factorial. That is 0.18. So 1 minus that answer, I am getting 0.8173. 0.8173. That is the probability that 1 or more customers arrive at the supermarket in less than a minute, in just 30 seconds. In just 30 seconds. Just 30 seconds. Just 30 seconds. I am going to do one more question. There are those questions that I put for you in the study text. I have only included the answers. So in your free time, you'll be in a position to go through them as you mark yourself. But I can help you, and we go through for purposes of mastering the concept. And we do that question 2. Then you do question 3, question 4, question 5. And if there are question 6, etc., etc., there are always many, you can do them. So question 2. Question 2 says, a life insurance salesman sells on life insurance policies a week. That is page what? 171. A life insurance salesman sells on average 3 life insurance policies per week. Use Poisson's law to calculate the probability that in a given week, he sells some policies. In a given week, he sells some policies. Number 2, 2 or more policies, but less than 5 policies. Number C, assuming that there are 5 working days per week, what is the probability that in a given day he will sell 1 policy? What is the probability that in a given day he will sell just a single policy? So let's try to answer that. So when they say that, what is the probability that in a given week, this person will sell some policies? This person will sell some policies. That simply means on average, this person sells 3 policies per week. And when they say some policies, that ideally means that the probability of error should be greater than a 0. The probability of error should be greater than, because they are talking of some policies, whether it is 1, whether it is 2, whether it is 100, but they are talking of greater than 0. In our analysis, we should not have a situation where we have a 0. That is what we talk of some policies. That means I'll have, again, on a number line, you'll be in position 2. This is 0, 1, 2, 3, etc. When they talk of greater than 0, we are looking at anything, probability of error greater than a 0, which is 1, 2, 3 going forward. 1, 2, 3 going forward. Going forward. So the probability of error greater than 0 is equal to the probability 1 minus the probability of error equal to 0, because that is the only one that we have where we cannot have any policies. Mutually exclusive. If we say greater than, then it simply means we are removing the probability that we can have 0 policy sold. Therefore, I'll have 1 minus the probability of this, it is e to the power negative 3, 3 to the power 0, 0 factorial. So that probability we shall have e. I believe we all have learned how to use the calculator to compute this Poisson times divided by 0 factorial. So it is 1 minus that answer, and the answer that we get there is going to be greater than 0 is equal to 0.9502. I hope that is the answer that we have in our study text. Some policies greater than 0. Simple. Part 2, 2 or more policies but less than 5 policies. 2 or more policies but less than 5. Now that one specifically, we are looking at the probability of 2 or more, but less than 5. So sometimes you can write this as the probability of 2 less or equal to x less than 5. So we want the probability that x is greater or equal to 2, but less than 5. That is how you would write it. That is how you would express it. That is how you would express it. 2 or more, but less than 5, which is equal to the probability of r equal to 2 plus the probability of r equal to 3 plus the probability of r equal to 4 there. And that means we have our e to the power negative 3 times 3 power 2 over 2 factorial plus e power negative 3 times 3 to the power 3 out of factorial plus e to the power negative 3 times 3 to the power 4 over 4 factorial. Your calculator has the ability to press that, to have that at once. So for me, I press e to the power negative 3 times 3 to the power 3. Is it 3 2? Divided by 2 factorial. So this is a 0.224 plus 3. Just change 3. This is 0.2240. Then when I change to 3, it's as if it's giving me the same power 3 divided by 3 factorial. Again, I have the same thing, 0.224 plus 3 to the power 4 factorial. 0.168. So 0.224 plus 0.224 plus 0.168. It gives us a 0.616. 616. That is the probability that we are taking. And lastly, assuming that there are 5 working days per week, assuming that there are 5 working days per week, assuming that there are 5 working days per week, what is the probability that in a given day you will sell one policy? What is the probability that in a given day he will sell one policy? Now, the 3 policies are for a week. In other words, in 5 working days, this person will sell 3 policies. How about in 1 day? What's the probability that he will sell, assuming there are 5 working days per week? In 5 days, this person sells 3 policies. How about in 1 day? You sell 3 out of 5 policies. 3 out of 5, which is equal to 0.3 out of 5, 0.6. Policies. Assuming that there are 5 working days per week, what is the probability that in a given day, just in a single day, we sell 1 policy? So our mean per day changes to 0.6. Our mean per day changes to 0.6, and having changed to 0.6, that simply means that the probability that this person sells just a single policy, if R is equal to 1, shall be E to the power negative 0.6 times 0.6 to the power 1 over 1 factorial. So get your E, power negative 0.6 times 0.6 to the power 1 over 1 factorial. Over 1 factorial. And I am getting an answer of 0.329. 329. 329. So that is how you would go about that. There are many questions there. Question 3, which first gives you a table and the frequency, and it is asking you to determine what's the probability of finding a sheet chosen at random which contains 3 or more surface floors. There, for question 3, you have to first determine the mean, and you know how to determine the mean where you have repeated frequencies. So, like, they are the normal questions. Please find them find the free time, and then look at question 3 and question 4. Question 3, 4, and 5. Question 3, 4, and 5. Let's look at Poisson approximation to a binomial. Is Hawa Mvanunji available? Please say yes if you're there.
Yes, I'm available.
I thought you're not attending. The binomial. Poisson approximation to a binomial. Poisson approximation to a binomial. Now if n, that is the sample space, if n is large, if n is large, and we said for when we mean large, a sample, a data set that is large, n should be greater than, n greater than 30. Like a data set is large or a sample space is big when it is greater than 30. If n is large, greater than 30, and p is small, less than 0.1, less than 0.1, less than 0.1, the Poisson distribution can be used to approximate to the normal, to the binomial distribution for calculating probability. This is what we mean, that where you find that a question has been provided, if n is large, n greater than 30, and p is small, less than 0.1, we can use a Poisson distribution to calculate questions relating to binomial distribution. That's what it means. That if you find that your n is large, greater than 30, greater than 30, greater than 30, and p is small, less than 0.1, then use Poisson distribution to calculate probabilities in questions from binomial distribution. That is what it means. That if you are being given a question and you're seeing that you have the number of times an experiment has been performed is finite, it is known with utmost certainty. Number two, you have a probability of a success, and you also have a probability of a failure. And then each experiment is having the probability of a success and a failure throughout in a given experiment. Like the probability of a success and failure are not changing. And also, we do not see any changes. There is no effect in the outcome of one trial affecting the outcome in the other trial. That question would point to a binomial distribution. But at some point, we are going to use a Poisson distribution because the n, the sample space that has been provided, is big. Remember, we said a Poisson distribution works in situations where we have a very large sample. And two, when the probability of a success, probability of it happening is very small, that is less than 0.1, less than 0.1, less than 0.1. So in such a scenario, we approximate using a Poisson distribution with a mean equal to NP and with a mean equal to NP. With a mean equal to NP. In fact, N is just that we need. Are we okay with that approximation? This means when you're looking at a question of binomial, sometimes you have to first test and see, does it meet the condition to use a Poisson instead of a binomial? And if the answer is yes, you have your probability of a success less than 0.1 and even the sample space is big, greater than 30, then go ahead and use a Poisson distribution. Go ahead and use a Poisson distribution. For example, example 1, we have some example there which says items produced from a machine are known to be 1% defective. In other words, the probability of a success is 1%, and 1% in terms of decimal points is going to be 0.01, which is less than 0.1%, which is less than 0.1%. If items are boxed in lots of 200, n is equal to 200. This is the probability of a success, meaning that the probability of a failure would be 1 minus 0.01. But any that has been provided, this is very big, greater than 30. So by looking at these two, the number of times this experiment is to be performed has been provided as the sample space, and it is equal to 200 boxes. But it is very big, greater than 30. But the probability of a success that a defective item will be found in those, it is very small, less than 0.1%, which is 1%. Therefore, by approximation, we use a Poisson to determine such probabilities. Instead of using a binomial, we shall use a Poisson distribution, because they are asking you to determine the probability that a single box has 2 or more defectives. 2 or more defectives. Therefore, instead of using a binomial, we shall approximate using a we shall approximate using a Poisson distribution. We shall approximate using a Poisson distribution. And in this case, we shall say that our mean, the average number that is required, is equal to NP, which is equal to 200 times 0.01, which is this NP. So I have 0.01 times 200, that gives us 2. So where they say probability of 2 or more, is it 2 or more? Yes, 2 or more, which is the same as the probability of R greater or equal to 2 is equal to 1 minus, since it is a Poisson, the probability of R equals 0 plus the probability of R equal to 1. 2 or more. I am not drawing the number line. I've been illustrating it. That is where I'm getting that. I am getting probability R equal to 0 plus the probability of R equal to 1, mutually exclusive. If we are talking 2 or more, we know that there are so many times 200 boxes. So we cannot have a probability of R equal to probability of R is equal to 0, equal to 2, 3, 4, 5, up to 200. You will have finished the paper, the question paper, by just doing that part. So if it is that, we use the other side, which is probability of R equal to 0 plus the probability of R equal to 1. So this would mean that we have probability of 1, which is equal to E negative 2 power 0 over 0 factorial plus E negative 2 power 1 over 1 factorial. Those are the only ones that I'm going to subtract, and then I'll have my answer. So I'll have 1. I have E negative 2 times 2 the power 0 divided by 0 factorial. This is 1 minus. Is Arnold available? Yes, he is. Yeah, I thought he has cut. So here we have 0.1353 plus 0.2706. So 0.1353 plus 0.2706. 1 minus answer. So my answer is 0.5941. That is my final answer. I have calculated, or I have solved a question coming from binomial, but using Poisson distribution. That is the approximation. If someone tries it using binomial, you find that you get the same answer, but it is important that you use only Poisson to solve questions where the sample space is very big, but the probability of occurrence is very small. Probability of occurrence is very small. Question 2, under that, from a haulage company's records, only 4% of deliveries are made in error. If 20 trips are planned next week, calculate the probability that there will be at least 2 erroneous deliveries using Poisson distribution. So use that. You'll be using that to do a Poisson distribution. Any question? Any question?
Excuse me, sir.
Yes.
Must the two conditions be met to use the Poisson method?
Normally, not necessarily. At least when you're looking at those two conditions, make sure that the sample space is big, because that is what that brings out Poisson. The sample space is quite large. However, there are questions under binomial, which you, if you so wish, that you can solve using Poisson. But a question which is under binomial and the sample space is very big, and also the probability of occurrence is too small, you must approximate. You must approximate. I know where the question is coming from the previous question. That question I'm asking you, the examiner is just being specific. But if you found a question of that kind, from a haulage company's records, only 4% of deliveries are made in error. You realize that if 20 trips is less than 30, it is only that here the examiner is being specific using Poisson. But if this question here using Poisson was not there, that capacity there, and you use the Poisson, you would be wrong, because the question points at a binomial distribution, because this 20 is less than 30, meaning that it is a small sample, and the question can be solved using binomial distribution. So a question that points at binomial and it is not looking at Poisson, don't attempt to use Poisson unless you're told to do so. But where the question is open and the conditions there are pointing at a Poisson, please use Poisson distribution. So my answer would be, for us to approximate, yes, the two conditions must be met. The two conditions must be met, unless otherwise, if the examiner points something different. That you see in that question. The question is a binomial, but is asking you to use a Poisson. Is that clear?
Yes, it is. Thank you.
Good. Okay. The normal distribution. 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 Now, Poisson distribution and binomial distribution, those two distributions we have looked at are discrete random variables, or are discrete distributions. A normal distribution is a continuous distribution. A normal distribution is a continuous distribution. We don't look at it as we don't look at it as a discrete, because a normal is actually a continuous distribution. Is actually a continuous distribution. Now, with normal distribution, we are saying that it is a continuous parametric distribution that bears the following characteristics. One, it is symmetrical about the mean, mode, and median. So one of the characteristics, we are saying that symmetrical about the mean, mode, and median. I am going to show you this, what it means. Number two, it is bell-shaped. In terms of illustration, it is bell-shaped. Number three, it is a continuous distribution. Number four, the area under the curve is 1. The area, or it can be proven that the area under the curve is 1. It can be proven that the area under the curve is 1. So in terms of illustration, it is going to be of this kind. We say it is symmetrical out the mean, mode, and so mean, mode, and median all found in one area. And we are saying that the area under this curve, the area under the shaded area here, is 1. Meaning that this side here, when you look at this line here, this is a 0.5, and even this side is a 0.5. So right from here up to here, this is a 0.5, and even this side is 0.5 in terms of probabilities, such that we get a 1 as our probability. As our probability. As our probability. So the total probability under that curve is a 1. That is normal distribution. Normal distribution. Now for normal distribution, we always say that we standardize the value of Z. What is that statistical value of Z? We normally say in statistics, a Z score, which we also refer to as a standard score, is a way to measure how many standard deviations an element is from the mean of a distribution. That's what it shows. A Z score shows a measure of how many standard deviations an element is from the mean distribution. Like how many standard deviations do you have? This element is from a given mean distribution. It's particularly useful for comparing different data sets that have different units or scales. And therefore, when we get to calculating the Z score, we say for a data point X, in a normally distributed population, for a data point X in a normally distributed population, with the mean mu, and the standard deviation sigma, the Z score calculated as Z equals to X minus mu over standard deviation. In other words, we are saying that the Z score will tell us how many standard deviations away from the mean a particular data point is. And if you find that the Z score is positive, the data point is above the mean. It means the data point is above the mean. And if it is negative, the data point is below the mean. And a Z score of 0 means the data point is exactly at the mean. The data point is exactly at the mean. So, having obtained the Z score of any value X of a normal distribution or of a normally distributed population with a mean mu and a standard deviation sigma, it is given by Z is equal to X minus mu over standard deviation. And the process sometimes is referred to as standardizing the XC value. Let's look at an example. Let's look at an example. Suppose the weight of a student is normally distributed with a mean, of 35 kilograms, meaning that my mu under normal distribution is 35 kilograms, and the standard deviation sigma is equal to 15 kilograms. Find the probability that the weight of a randomly selected student is more than 50 kilograms. Find the probability that the weight of a randomly selected student. Now, a randomly selected student is the X. A randomly selected student, which is X, is more than 50 kilograms. Remember, we said we shall have a data set point. Okay? How many standard deviation this point is away from the mean. So they're asking us find the probability that a weight of a randomly selected student is more than 50 kilograms. So the weight, how many standard deviation is it away from the mean? And remember, the mean here is 35 kilograms. And so with that, when we try to standardize the value of Z, as we try to standardize, we shall be getting the probability of X greater than 50 kilograms, which is equal to, of course, we have X minus mu over standard deviation, So I'll have P X greater than 50 kilograms, which is equal to X is 50 minus mu, which is 35, out of standard deviation of 15. Out of standard deviation of 15. Which is 15 out of 15, giving us a 1. Giving us a 1. So our Z, we are going to get probability of Z greater than 1. Z greater than 1. That is what we want. We have standardized our X in terms of Z. So our Z, it is the probability of Z greater than 1. Remember, this must be illustrated. You can have it illustrated. Our mean is a 35 here, meaning that the fit is, because it is higher than the mean. Kg. And finding our Z, we realize that our Z is a positive. So this fit is in form of X. So in form of Z, this fit is equal to 1. Positive 1 in form of Z. And it is positive. Remember, we said our Z can be a plus or a minus. Z can equal a plus or a minus, depending on the mean value and the X value that has been provided. So when they say greater than 50 kilograms, and the Z value which represents a 50 is here, greater than, this is where we have our 50 and 1. So greater than shall be this side. We employ this side. But don't forget, from here up to the end, it is 0.5. Now, if I come here up to this side at the end is 0.5, and I don't know this part that I shared, it's like getting something of this kind. I divide this. From here up to here, it is 0.5. But from here up to here, it is X. It is not known. It is not known. Can't I find this, given that the whole of this is known? That is what I'm asking myself. So, meaning that if I do that from here up to here, now that would mean if this is x, then from here it's going to be 0.5 minus x. The same applies if you know that this was x, then this one is 0.5 minus x, depending on what you want to get. So in this case, it would mean I get 0.5 minus x plus x, which is 0.5. So ideally, that is what I am supposed to use to ensure that we actually ascertain the total. So what we are going to get here, it's going to be 0.5 minus whichever probability that we are going to get, because very soon we are going to obtain the probability which is here. The table that we use to determine this probability that is here is provided. I don't know whether I can get one of these and I illustrate, because members, I think you can see. I need to have a past paper. I need to have a past paper, a QT past paper, and make an illustration, and I show you, because members normally fail to read off these. There is a way you fail to read off. Assuming I look at paper 3. Okay, I want to get a past paper. A past paper, where can I find it? Let me get to WhatsApp. Zoom, come. I'll share after. I don't want people to see my WhatsApp. Means okulaba bimutaina kulaba. So I am getting a past paper from my WhatsApps. The local government thing. Oh. Uh-oh. Okay. I can now get back to Zoom and I share. So assuming this is a past paper, and I'm interested in seeing this here. When we get the tables, here's the tables. How we want to know that is the kind of table I have to use. Do you see this curve? The table is the cumulative node distribution P in bracket Z. The cumulative node distribution P in bracket Z. In bracket Z. Meaning that this is a table that I'll always be using for normal distribution, and it has a curve of this kind, it is showing using this arrow P. Every time you use normal distribution, you'll be getting this P shaded. This shaded part here, it is the part that you'll be getting. That is the ZP. Every time you're using normal distribution, whichever probability that you're going to get, it is going to be for this part that is shaded. And if it is negative, then it will be this other side, the opposite side of P. Again, a shaded part which is around that place, but in the negative bit. And we are saying that the Z value that can be obtained stretches from -3 to +3. -3 to +3. So you have +1, +2, +3. In terms of Z, so your Z can never exceed +3 or it can never exceed -3. It is supposed to be in that range, -3 to +3. So whichever value using normal distribution as you compute, if it is a +1, +2, +3, -1, -2, you'll be looking at this shaded part. The same way P appears here, it is exactly the same way P can appear this other side, but in negative values. So our P can be a positive or a negative. And whichever value or probability that we shall be calculating shall be for this Z, this P value which is calculated, or the P value in form of a negative, which shall be this other side. Now, if I have my P here, for example, if I have my table moving this, I've illustrated this here. Where I done it. $28 doesn't have anything. Where did I get a -1? Have I removed them? I am seeing where I've been doing it anyway. I can say it was P, the probability was Z score is equal to 35 minus 50 over 15, something that gave us 15 out of 15 to get a 1, +1. We made an illustration. We made some illustration here. And we said that this is 35. In terms of X, here we have 50. In terms of Z, we say this is +1. +1. We are interested in getting the probability when the weight is more than 50. So the 50 is there, so the more than is this side here. But the table or the curve I have can only allow me obtain the probability that is in this part here. Where you see those lines moving vertically. That is the only probability, or where we see those zeros. So the table, this table that has been provided can only allow me obtain that probability. And if it has not, it is not giving me that, then I'll be getting this probability. The one is other side here for this cheap part. That is if the Z value is a negative value. If we are getting Z value as negative, then we shall be obtaining this probability. If it is positive, then we are getting this part here alone. We are getting that part there alone. That is what gives us this part that is shaded. If the Z value is positive, then it is, we are calculating, we have a value that we calculate is for that. If it is negative, whichever value we are getting, it is flat. And we know that from here up to end is 0.5. So if I have this, can't I obtain this? The part which is remaining? The answer is a yes. So having done that, it means I'll get to the table because I have seen my value is a positive 1. So if I get to the table, can I find the probability that relates to positive 1? I'll come here and check. The Z value, we are saying that it is a positive 1. Look through the Z value. Do you see anywhere where we have 1.0? This part here. 1.0 is here. Oh, so 1.0 is here. So 1.0 with 0 values or 0 values of Z, no additions, I'll have a 0.3413. Do you see that? 0.3413. It is here. I don't know whether you guys are my cursor moving. You see the cursor? 0.3.
No.
It is 0.3413. So the 0.3413 is here. I am saying that Z is equal to 1.00. So it is this one here. Do you see my cursor?
Yes. We can see.
So this is the value here. I can't make any changes. I cannot, because this is a document, a different document which cannot be edited. So I have that as my, because I have read through the Z value, I have 1.0, and then I have a 0.3413. So having gotten that, I'll be like, this probability here, in this region here, it is a 0.3413. 3413. So that is what I'm showing you. You have from here up to there 0.8. You have X, but this was 0.3413. Can't you determine X? You can by simply saying that 0.3413 plus X is equal to 0.5. So it means 0.5 will be, we subtract 0.31, 3413, and our X will be that. So you'll be in a position to get your 0.3413 to have your X as equal to 0.1587. That will be your X. Now that is the probability that I'm interested in. That is the probability that I'm interested in, because we are saying that we are getting the probability when it is more than. So I'll be getting, normally what we do, as you have this curve, this is Z, which is equal to 1. This has given us 0.3413. And the examiner is interested in getting Z greater than 1, which is equal to 0.5 minus 0.413. 0.158. That is the probability. That is the probability. That is the probability. So there are many more other examples which we shall be looking at. I see it is 5:16. I want to end here. Any question? Any more questions? So if there are no questions, I want members to start practicing these numbers. We have quite a lot that we are supposed to look at tomorrow. Probability numbers from these three areas, these three distributions, and then permutations and combinations, and then calculus and calculus questions. Members, make sure that you appear tomorrow because we are going to look at so many questions, and those are so many questions will indeed help us, especially in understanding this area of probability. So I expect you to be there. At 2, we shall be at school, and the class will start at exactly 2. Whether I have 1 student or 2 students, at exactly 2, I'll be starting the class because it is a revision class, and I do not know whether all of us are going to appear. So whether I have 1 student or 2, at exactly 2, we shall be starting our class. If there are no questions, please have a nice evening, and thank you for attending. I'll share the recording, and then those of you who have not attended, those of you who have not understood some places, you review. Thank you so much. Have a good evening.
Thank you too.
Bye-bye.